Okay. So what were we talking about last time? Yeah, we were talking about the Pauli exclusion principle, and we were trying to come up for a wave function for helium, right? And then we had these possibilities. Whoa. Oops. Where we had to make the orbital approximation. And this, what's this portion of it? What type of orbital? 1s, yep. We called this one the spatial orbital. What was this thing? Because now we're beyond one electron systems, we have to account for spin. We were pretending we didn't know anything about the Pauli exclusion principle. And we had these as our possibilities. It's in a bit different order than we wrote last time. Geez. Okay. We know which two are not going to be the answer, right? Which two are not going to be the answer? Yeah, top one and the third one, why aren't they going to be? Yep, same spin. Since electrons are fermions, the exclusion principle states you can't have the same set of quantum numbers. These two would have the same set of quantum numbers, so they're going to go away. Okay. But they didn't know that at the time. But what they did have is some experiment, and they looked at the spin state of helium. So they could shoot helium through a magnet and figure out, hey, was it perturbed by the magnet? Helium, would it be, like, is this system paramagnetic or diamagnetic? Yep. Yeah, it's diamagnetic. So is it going to really respond much to a magnetic field? No. So they knew that. So, however, two of these functions are experimentally observed. And the total angular momentum was equal to 0. Okay, which of these have a net spin? So A, B, yep, A has an overall spin, so that one's gone. What other one has an overall spin? Yep. So we can eliminate those two possibilities. So B and D, the only possibilities. So that's where they incorporated some experiment into this. Okay, so now we have two functions. Now the question becomes, which one's the right answer? If we select one of these only, what ends up happening is we know the exact spin state of the electron. And by the mathematics, we're actually not permitted to know that. So we can't say electron number 2 is definitely beta, because we can't tell 2 and 1 apart from one another, really. Like, we don't have a little itty-bitty microscope to look at them. They don't have different colors. It's just as probable that 2, let's call beta spin down, 2 and 1 both have equal probability of being upspin or downspin, right? So if we select 1, then we know the exact spin state of the electron, and this is impossible. Because we can't actually tell those electrons apart. We know that there's a net spin or no net spin. So then let's look at the question of how do we deal with this? Oh, did I leave my book? Oh, no, there's my book. Okay, so did we talk about Schrodinger's cat in here at all, or no? Okay. It's a weird thought experiment, and it was initially thought up of by Schrodinger because he actually hated his wave equation and he didn't really believe it. The way it works is you have a box, you put a cat in the box. There's my cat. I've been spending way too much time with Scarlet drawing cats. There's my cat. Thank you. I'd say, you know, when you're sleep deprived and trying to have forced to draw little animals, you get okay at it. But I don't like that line. There we go. Now, what we do with the cat is we put in some radioactive cesium, and we have some poison in here. The poison's in a sealed vessel. If the vessel breaks, it will kill the cat instantaneously. And now we have the cesium atom lined up to a Geiger counter that has a hammer. It's a shit hammer. Oh my goodness, what am I trying to do here? Hammer. There we go. That's meant to be a hammer. Okay. If the cesium atom decays, it will spit off a particle, the Geiger counter will read it, and it will break the vial and kill the cat. Now, what we do is we cover up the box. Do we know if the cat's dead or alive? No. The only way we know is by looking, taking that top off, and observing. So we could actually write a wave function for this cat. We have to have a normalization constant. And what are our two states that are possible? Yep. You have the alive plus dead. Now, this is a superposition, right? The cat has different probabilities of either being alive or dead. When we take off this thing, what we're doing is we're collapsing the wave function into one of these two possible states, either dead or alive. So this book is what I learned quantum mechanics from in my physics classes. where it has a picture of a live cat on the front, dead cat in the back. The weird idea behind this is it's not the sicko who set up this experiment, it is you who kills the cat. So as soon as you remove that thing and you observe what's happening here, you collapse the wave function into one of these two possibilities. So if you open the box and the cat's dead, you killed the cat. Okay. What it really was to highlight how ridiculous this whole idea about like wave functions and stuff was. Schrodinger really didn't like it, but then it kept working, so people kept running with it. Yes, he had a lot of issues. I don't know why I picked a cat instead of like a rat or whatever. I think it's because some people really, really like cats, so it was like trying to make you feel bad for killing the cat. But what this actually is a linear combination. So just like us, we have two possibilities, right? We either have electron number 1 is alpha, electron number 2 is beta spin, or the opposite. Those are our two possibilities. So if we want to get around saying which one's which, we just say, hey, we have a linear combination. And if we do that, then we're okay. We're not saying one is indistinguishable from the other. So, and we can construct wave functions for helium from a linear combination. So we have two possibilities. We have one where they're symmetric. And then we have asymmetric. Or antisymmetric. Now, just like over here, we have to have a normalization constant, so that's where this number is going to come from. And now we have this as our option. Then we have number 2. What is our other possibility? Yep. I'll put this in square brackets, sorry. Okay, that's an example of a symmetric wave function. An asymmetric or an antisymmetric system, instead of having a plus sign here, we'd have a minus sign. Okay, but now we're at a problem. We have two wave functions. One has to be right, one has to be wrong. So our question is, which psi is the right one? So in order to do this, we have to fall back to the Pauli exclusion principle, or the Pauli principle. Where it states that wave functions, if you change the labels, you get a negative sign. So if I had psi 1, 2, how is the relationship between 2 and 1? Yeah, that has to be true. That's known as antisymmetric. Where would that be true? So if I switch these two labels, does it change the function at all? So swap it. 2 goes here, 1s go here, 2s go here, 1 goes here. How about we you don't have to write this part down. Yep, these would be the same if you switched the labels. However, if we did it with the other one, what's going to happen? It'll be opposite. You'd have to pull a negative sign out front to make them equal with one another. So, therefore, that's our solution. Okay. Is this really all that bad to write out? What happens if we introduce one more electron? It's going to be bad to write out because not only do we have to worry about the 1s, but what else will we have to go up to? 2s, and then the 2s could have electron number 1 or electron number 2 or electron number 3 in it, and it becomes just a giant mess. An easy way to represent this, easy, as a Slater determinant. I'm going to keep that because that's what we're going to try to represent. So basically what we want to do is take this and go back to a determinant. So we'll have 1 over square root of 2. How many, actually I'm going to probably need more space than that. Let's see. How big of a matrix will I need here? Or how big of a determinant will I need here? Yep, it's going to be a 2 by 2. The first column we generally deal with alpha spins, then we do beta spins, and we keep going back. So we'd have 1s1, alpha 1 here. 1s2, alpha 2. What would the next column have? Yep. And of course, I didn't give myself enough space. What about this guy? One. Yep, 1s2. Yep. Okay, remember, if you were to evaluate this thing, what would this guy be paired up with? Yeah. And what would this one be paired up with? Yeah. Oops. And they're subtracted between one another. So this is kind of an easier way to represent this wave function. If you have a multi-electron system, am I okay to erase this bit? In general form, one, two, and you have some system that goes to n number of electrons. You have 1 over square root of n factorial. Sorry, try to go through this. We start with alpha 1, alpha 2, then it continues on to alpha n. What would the next column look like? Yep. One S2, beta 2, dot, 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 n, beta, n. And that would continue until you got to whatever orbital you need to get to. We're going to label it with M. And depending on where we ended, we might either have to go to alpha or beta spin. Does that make sense? Okay, so that's how these wave functions are represented. Oops, yep, you would have a px, py, pz. If you only need to fill one of them, you would go up to 1. Let's look at an example. We're going to have you do the determinant for lithium. Okay. Am I right to erase this? Okay, so example, construct the Slater determinant for lithium. How many electrons will lithium have? Yep. I like to indicate the atom I'm looking at that way as a subscript. Okay. What comes next? Yep. You're being more mathematically formal than me. I just leave it as 3 factorial. How big of a matrix are we going to need? Excuse me, determinant. Yep, a 3 by 3. What's going to go up here? Yep. Yep. Then if we move over, it's still 1s, but what spin do we need next? Yep. What about the third column? Yep. Because we've filled that 1s. What numbers are going in here? And then what about spin orbital? Yep. Does it really matter? No. So if you put beta in here instead, works out to be the same. But that is an important point. For like when you look at excited states, there are possible permitted excited states depending on what experiment you're doing. But for us right now, it doesn't matter. Okay, what's going to be the next column? Or row? Yep. Yep. So we're just replacing all the 1s with 2s, right? Oops. And then the last row. Yep. Replace the 2s with 3s. So you can use this to figure out the Slater determinant for any atom you're interested in. And that represents the wave function of that atom. Okay? That's going to be a Quizlet question. It's probably going to show up on an ACS exam. Did it show up on the practice one?
No, I think the only one was that one that was the
Huckel. Yeah. Yeah, we'll get to Huckel in a little bit. Feel pretty good on that one? Feel like you could do it for, I don't know, beryllium? Yes, that's one of your daily problems. And then I asked you for an excited state, I think, of helium. What's that? I'm not telling you. Am I okay to erase this? Yep, I want you to think about that one. But honestly, again,